this lecture, I'm going to go ahead and explain what genetic pedigrees are. Now that we know how chromosomes are passed on from generation to generation, we can put everything together into a pedigree, which is basically just a fancy way of saying family history. So before we go ahead and try and put together an example, let's go ahead and take a look at what the key looks like, what the designations. So the way it works is that all males are indicated by a square, and all females are indicated by a circle. Okay? Then you have two different types. You can have them empty, like the two are that I just circled there, or you could also have the square and the circle filled in. If they're filled in, we call these affected individuals. Now that's kind of an interesting word. Affected means, could mean you have the disease. So for example, you have hemophilia. So we'd know that you're affected and we'd color you in there. But affected could also mean that you have some trait. For example, baldness. So like myself, I don't consider it to be a disease, but I am definitely affected. And by affected, we mean you can see it. You can see the phenotype. Sometimes they might be a carrier, might be in there, but we don't know yet. If we go ahead and have the two connected here, like I have down here, that means that they are mated, husband and wife, shall we say. And if they have children, we would then draw a line from them to indicate their children. So here and here. Okay. Now every time you drop down from here, say to here, that indicates we have another generation there. For the examples that I'm going to talk about, we won't worry about twins. Okay, so that's how we define our terms in a pedigree. So let's take a look at this one here. Now this pedigree has three different generations here. There's the grandparents, there's the parents, and there'd be the kids over here, generation 1, 2, 3, going in this order. You can see that granddad over here and grandma, they had 3 children, 3 sons, and then this son here got married, and he and his wife then had 3 daughters. Now you can see that we have an affected individual here, 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 and here. Okay, so if you go into a genetic counselor, they'll ask you who your relatives are and so forth, and put together a tree like this, and then they start to fill in the circles. Now, when a genetic counselor sees a lot of circles filled in, they assume that it must have been a dominant trait that causes this disease. In particular, if you see that there's an affected individual at every generation, the likelihood is it's a dominant trait. Now, you never really know for sure. And one of the problems of doing human pedigrees is that, unlike so many other animals, we don't have dozens of children at each level there. So the genetics and the probabilities are hard to do. The more people you can get, the better information you have, and the more likely that your diagnosis is true. An example of a dominant sex-linked gene would be Huntington's disease. So in this case, this is a dominant trait passed down generation to generation. Now here's an example of a recessive. Now once again, we've drawn in all the people in the family tree, and we've circled in, darkened in the ones that are affected, and you can see that there's a generation here, up here, where we do not have any affected individuals. In particular, you'll notice that if you have 2 people who do not have the gene, and then they go ahead and have a child who does have the disease, that's probably a really good indication that this was a recessive trait, because these 2 people probably are big A, and big A, little a, right? And therefore, you finally got a recessive homozygous down there who showed the disease. It's the only way that could have really happened. Once again, if you see the trait at every generation, probably dominant. If you see a generation missing, in particular, 2 unaffected individuals who have a affected child, probably a recessive pedigree. A good example of a recessive trait is cystic fibrosis. Okay, let's take a look at one that would be sex-linked. So this is a trait which is on the X chromosome. Now we have a really big family here, lots of people to choose from. What do you think? Is this a recessive or is this a dominant trait? Well, since we don't see it at this generation here, and since you have two unaffected individuals who then have affected children, it's probably a recessive trait. The other thing, too, is we can see that this is probably sex-linked. What does it mean by sex-linked? If you have an unusual number of boys who have the trait, it's probably on the X chromosome. And in this case, of the 4 people who have the disease, muscular dystrophy, we can see that they're all boys, probably an X-linked recessive trait. Okay, what is the likelihood of a child having a disorder? You have to do a pedigree. The more children you can find there that you can fit in there, the more likely your conclusion is. Finally, let's go ahead and try an example using my family here. So, suppose my wife and I are thinking of having a third child. Right now we have 2 children, 2 boys. What is the chance that that child will be nuts? Okay, here's my family tree, and believe me, lots of nuts in my family tree. So I'm over here, there's me, there's my wife. The affected individuals, the nutty people, are in dark. So my wife is nutty here, my son is nutty here, my wife's sister, definitely nutty, and my wife's mother, that is my mother-in-law, also nuts. On my side of the family, my mother also is kind of wacky. Very good. So, what do you think? Is this a dominant trait or is this a recessive trait? Well, we see one in every single generation, so the likelihood is that it's probably a dominant trait. We don't know that for sure. You can't find that out for sure. You got to have more people here, but we also see here that over here, 2 unaffected individuals only have unaffected children. So chances are this is a dominant trait. Okay, if it's a dominant trait, right, that means that I must be recessive homozygous, and my wife has to be dominant, right? And also, if we have children who are both normal and affected, she must have been big A, little a. So she's a heterozygote, but the dominant trait shows the disease. Okay, that means that my nutty son over here must have been big A, little a. My normal son must have been little a, little a. And what is the probability that we would have another child who would be nutty or normal? Well, it could be normal if it's little a, or it could be nutty if it's little a, big A. So the chances are, based on our analysis, 50%. Finally, what do you think? Is this a sex-linked trait on the X chromosome or is this autosomal? Well, we don't see a high number of boys affected here. In fact, we see out of the 5 people, 4 of them are girls. So we would conclude based on this that this is probably an autosomal, a dominant trait. And this would be an example of doing a pedigree for them.